Hello, physics. At MBA, it's pretty often hard to show anything about static electricity because it's so moist here. But today is a bright, sunshiny day, and we can do a little bit of demonstration today. So I have here a balloon, and as you can see, if I rub it on my head, it attracts the hair, and that's some static electricity. In fact, whoops. If I rub it a bunch, I can even get it to stick to the wall. Now, I'm using the ruler here to give it a little bit of help, but it's staying there due to static electricity. If I don't give it a little bit of help, it falls down. Because MBA does not handle static electricity very well. But here we can do a little bit of demo with this. So let's talk about static electricity and electricity in general. Hello, physics. This is starting chapter 16, electric forces and fields. And we're going to look at electric charge. So our section talks about electric charge and just what is it. And they give you an example of on a dry day, take a rubber balloon, and rub it on your head. And you will see some static electricity. And if you have a good dry day, you might be able to have it stick right on the wall. Here, we live so close to the ocean that it's very hard to get it to work very well. And today happens to be a bright, sunshiny day, so that's why there's some demonstrations in this video. But otherwise, it's very hard to get static electricity to work. Now, it's very important to understand that like charges repel. Now, jumping across here to understand how we get charges, as you'll remember, atoms have a nucleus made of neutrons and protons, and the protons have a plus charge, and then the electrons going around them have a negative charge. Well, if we can take this electron away and put it to some other substance, we can make that have more negative charge, and this would have less. So that ends up with a net positive charge, and the other substance ends up with a net negative charge. And this happens on the order of hundreds of billions. And here's an example of the surface of the balloon and some hair. And the balloon is considered to be negatively charged, and the hair is considered to be positively charged. So the balloon has taken some of the electrons from the hair. Now, with the opposite charges, what's the net result? There's an attraction. And that's why you can see here that the hair is being attracted to the balloon because the opposites attract. Now, by the same token, if we were to take two balloons, rub them together, and get the opposite charge on them, they would then repel each other and not be attracted to each other. And so you can see in a demonstration that if we have the two metal leaves and we let the charge get onto both of them, they will be repelled apart from each other because they both carry the same charge. So that's why over here it talks about that like charges repel and unlike charges attract, opposites attract. We can blame Ben Franklin for calling it positive and negative. And they say by convention, hair is considered positive and the balloon is considered negative. And since they're opposite, they attract. Now, for some time going forward, in our book, a positive charge is going to be represented by a dot here with a plus on it. Negative charge, a negative blue dot. And electric field, this is the direction of the force. And this is when we have a bunch of field lines, we can show that. You might not be able to tell, but you can look in your own book. There's little arrows on here trying to show the direction of the charge or the field. Now, a famous experiment in 1909 done by Robert Millikan. He did this experiment where he sprayed fine oil droplets into this chamber or this apparatus here. And he had a plate in the middle with one tiny hole. Using a battery, he would put a charge of plus or minus on these two plates. And then he could take a microscope and he looked in here and he could see right there a very, very small dot. And that dot is representing a drop of oil. And depending on the charge put on here by the battery, he could make that oil drop go up or down as it's repelled or attracted by the two different plates. Even though gravity is trying to pull it down, he could keep it from falling all the rest of the way by putting a charge on these plates. And after doing that many times and doing a lot of careful measurements, he found that an object is always a multiple of a fundamental unit of charge. Kind of like what we saw in chemistry with you don't have half an atom, so you can always have multiples of whole numbers. And the same kind of thing is true here, although it's so small, it doesn't feel like it. So the idea is that the amount of energy is quantized. It's in chunks of multiples of the charge on what we know and understand to be an electron. Millikan demonstrated that the electron has a charge equal and opposite to the charge of plus E, which is the value on a proton. And the value E has since been calculated to be 1.602 times 10 to the negative 19 coulombs. And a coulomb is the SI unit for electric charge. All right, we're going to round off in our book we're going to use this here for our charge. And you may want to make a mark here in your book, because even in other chapters, we're going to have to come back and use this number several times. So that's a number we want to remember. The mass of an electron is extremely small, times 10 to the negative 31 kilograms. And on that small object, we have this much charge. Well, keep in mind also, if we have this much negative charge on each electron, well, what do you suppose we have on each proton? The equal and opposite charge. Most of the time we're talking about the electrons, so that's why we have that number marked there. All right, so how do we transfer that electric charge? When we did the talking about the balloon, we're actually having electric charge that's separated and not moving. And the word that means in English not moving is static. So static electricity. But we like electricity to do jobs for us. And when we can make it move, then it'll do a job for us. So we have some materials that will conduct electricity very well, and so we call those electrical conductors. Things that do not conduct very well, such as glass, rubber, silk, and so forth, they're called electrical insulators. Around here in California, a lot of times because of fire season, they will put big towers on top of some of the mountains where people stay and constantly watch to see if a fire has started. And that's also likely a place where lightning will strike because it's the top of the mountain. And a lot of times in those buildings, they will actually put glass chairs for the employees to sit on when there's a thunderstorm, so that if lightning hits the building, the glass chair will insulate them and they will not be killed by the lightning strikes. Now, some things are conductors, some things are insulators, and some things are halfway in between, semiconductors. And they are somewhat between insulators and conductors. And by using this in some substances like silicone and germanium, as you might remember on the periodic table, that zigzag pattern on the right side of the periodic table between the metals and nonmetals, that is the area we call semiconductors. And we use those in a lot of electronic devices, phones, TVs, computers, and so forth. If it weren't for those things, at this point, we wouldn't have any of those, what we call technology. There are also other things that are not only conductors, but really conduct, because everything that conducts, there is sort of resistance. Well, I'll compare it to like friction. But so that when electricity goes through a wire, copper or something like that, it goes very well, but there's still some resistance. And just like friction, that resistance in the wires will create heat. And we lose energy in that process. Well, there are some materials that conduct very, very well and have actually a zero electrical resistance, which is really kind of strange. It's like saying we have two substances that can touch each other and have zero friction. There is no such thing. But in electricity, there is. There are some things that have zero electrical resistance. The electrons flow freely. And all the substances we know now have to be below very cold temperatures. So you have to get them super cold, like colder than liquid nitrogen or colder. And if you can figure out how to make a superconductor that works at room temperature, pretty confident you will be a wealthy person. So that might be an area that you want to work on, is to figure out how to make a room temperature superconductor. At this point, most of them work at super cold temperatures. This would be good in, say, technology for a bullet train or something like this that can go super fast and not lose energy. The last part of our section talks about grounding and inducing a charge. And we're going to talk about grounding first. So grounding is very important. When there's an electric charge, this is trying to look at an individual picture. So if we were to get a piece of rubber, like a balloon, and have a negative charge on it, it would then come and push the like charges. The electrons are going to push away those electrons. They want to be away from each other. So in this other substance, it's going to push away those electrons. And so what ends up happening is that this has an opposite charge. There's going to be a net attraction, even though this object was not charged in the first place. But see all those electrons? If it's grounded, they have a place to go. And this is a symbol in electricity that we show it's grounded. Grounded meaning those electrons have somewhere to go, usually something big. It could be the earth, could be a pond, anything big. There's plenty of place for electrons to go. Every house, every building has a grounding for it, among other reasons, in case it gets hit by electricity. You have to run the wires to like the foundation or something like this to give the electrons a place to go, so that the charge doesn't build up and go somewhere where you don't want it to go. The other example here is where you bring the object here, the electrons go away from that object. There's still an attraction, but those electrons don't have anywhere to go. And so when you take the object away, why you have them balanced back out in the charges. Whereas this one lost some of those electrons and ends up with more positives than negatives. So we have both concepts here of induction and grounding. So I'm going to illustrate inducing a charge, kind of like what it talks about here in our book, inducing a charge, where we can take a charged object and force the similar charges to leave and attract the opposite charges. I'm going to use a magnet to do the same kind of a thing. So I'm going to, you can see that this paper clip, none of them are magnetic to each other, but if I take another magnet and bring it nearby, it can induce a charge into the magnet and then be attracted to other paper clips. And you'll see that even if I take the magnet away, it still has this magnetic attraction, and it's because it induced it. Now if I take it apart and then try to put it back together again, let's rub it good, then it won't stick anymore because the charge is gone. The same thing happens with electricity. If we ground it, there no longer will be the opposite attraction and things will not stay attracted to each other anymore. And that concludes our section here, chapter 16.1 on static electricity and conductors and so forth. So Mr. Engel is going to rub some static electricity here, separate electrons, and then he's going to take it and put it over on, touch over here these metal leaves, and you'll see that they're going apart and coming back together. And the reason they're going apart is because that balloon now has one charge, and that charge is being conducted down into this apparatus, and both of those pieces of metal are getting the same charge. Well, what happens when you have the same charge? The same charges repel, opposites attract. And this is our evidence that we have some static electricity, that they're all of the same charge. All right, you videoing? Mm-hmm. I want to show you the setup here. This is a 2x4 on what's called a watch glass. So there's a piece of glass here. So the whole thing is balanced. Let's see if I can get it balanced again. So that it can pivot pretty easily. And then we're going to take a balloon and I'm going to get some static charge on it and see if I can attract this 2x4 with the static electricity. You can see that I'm pulling it with this balloon. Not touching it. That's it.
Ooh, that's good.
You're too far away. Come a little bit closer. Might have to scoot the chair a little bit. Yeah, there you go.
Still pushing it down.
There we go.